Hi. So in this video, we're going to take a little bit more of an algebraic look at what's going on with limits and how to evaluate them. First thing we need to look at if we're going to do this, though, is we need to see about some properties of limits. We want to look and see what we can and cannot do with limits. So here's a list of some properties of limits. Let's go through these really quickly. The first one is actually 2 in 1. It actually says that the limit as x approaches a of one function f of x plus or minus another function g of x is the same as or equal to the limit as x approaches a of the first function plus or minus the limit as x approaches a of the second function. Basically, what we're saying here is that the limit of the sum is the same as the sum of the limits. Okay? What that allows me to do is it allows me to break these functions up. If I've got something like x squared plus 3x, then I can find the limit of x squared and I can find the limit of 3x, and then once I have the two of those limits, I can add them together or subtract them depending on what the operator is between them. So it allows me to break these functions up into smaller pieces. Same is true about the limit as x approaches a of f of x times g of x. I'm also allowed to look at the limit of the first function times the limit of the second function and then multiply the result of that together. So the limit of the product is equal to the product of the limits. Our third property here is that the quotient of the limit of the quotient is equal to the quotient of the limits. So the limit as x approaches a of f of x over g of x is the same as the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. So I can look at those independently. One caveat with this, not surprising that we have to make the stipulation, this is only true if the limit as x approaches a of g of x exists or is not equal to 0. We got to be careful about things like that. The last one here, the limit as x approaches a, c is a constant, so if we have the limit as x approaches a of c times f of x, then we can pull that constant out of the limit because it's not being affected by any x value there, so it can slide outside of the limit and then find the limit of the function, multiply that times the constant. So if I had something like the limit as x approaches a of 3x squared, I can pull out the 3 and make that 3 times the limit as x approaches a of x squared. So those are our basic properties for limits. Sometimes you'll see questions like this that don't have any functions to evaluate or anything. They'll just tell you the value of this limit is 4, the value of this limit is 3, what's the value of the limit as of f of x times g of x. So they kind of keep it generic. You might see some problems like that. Really, that's just an application of these properties of limits right here. Nothing really surprising here, nothing out of the ordinary at all. So hopefully that won't be a problem at all. So what we're going to do here is we're going to look at some simple problems to begin with to see if we can find the limits for these things. The first thing when you're evaluating a limit algebraically is the first thing that you always want to try is just plug in the value. So if I've got something like the limit as x approaches 4 of 3x squared plus 2x minus 1, the easiest way to evaluate this is to simply plug 4 into this function. If I get a value, there's my limit. So in this case, I could do, that's going to be equal to 3 times 4 squared plus 2 times 4 minus 1, which of course be 3 times 16, which is 48, plus 8 minus 1, which is 56 minus 1, which is 55. So my limit of this is going to be equal to 55. So this is the easiest way to evaluate a limit. Just plug in the value. The problem starts to come about when we plug in the value of the value for the x, some interesting or weird things happen like division by 0 or something like that. So we've got to be careful about those kinds of things. So let's take a look at how we would handle situations like that. Let's say that we have, grab my sheet of paper here so I can write this problem down right. Let's say that we have the limit as x approaches, let's do x approaches negative 3 of x squared plus 2x minus 3 divided by x squared plus 5x plus 6. Okay. Now, like I said, the first thing that we're going to want to do is we're going to want to plug in negative 3. I'm not going to go through the process of doing that here. I think we can quickly figure out this is going to be 9 plus or minus 15 plus 6, which is going to give me 0 in the denominator. Actually going to get 0 in the numerator as well here. I'd get 9 minus 6 minus 3, which will also be 0. So this turns up to be 0 over 0. It actually does tell me something. It tells me that I'm going to be able to algebraically manipulate this thing and get rid of the problem that I have at -3 so that I actually can evaluate this. So the way we're going to handle this is we're going to do, you can do whatever algebra works. Okay, as long as you've got an algebraic method that simplifies this function, we're allowed to do it. I can do any kind of algebra I want. In this case, since these are both quadratics, I'm going to take both the numerator and the denominator and I'm going to factor them. And if you notice, the top one's going to factor into x plus 3 times x minus 1. And then the denominator is going to factor into x plus 2 times x plus 3. Now, the reason that this is important for us is because, remember, we're looking at what's happening as x approaches -3. Normally, we wouldn't want to cancel out things in the numerator denominator that have variables because we're eliminating solutions when we do that. But in this case, I'm going to go ahead and do that. And the reason that I'm going to go ahead and do it is because of the concept, the idea that we were talking about in previous videos, where I don't really care what happens with this function at -3. I only care what's happening around -3. And so when I eliminate this, when I cancel those x plus 3's, I'm taking out something at a point where I'm really not interested in what's going on anyway. I don't care what happens at -3. I only care what's happening around -3. And so now I can simplify this and say, okay, now I want the limit as x approaches -3 of x minus 1 over x plus 2. And now I can go ahead and plug in -3 here. That's going to get me -3 minus 1 divided by -3 plus 2, which is going to get me -4 over -1, which is 4. And so there's the value of my limit. My limit is equal to 4. Okay, a couple of things that I want to point out here along the way. I've already made hopefully a big deal about being able to cancel the x plus 3 and why we can do that, because we don't care what's happening since we're working with a limit at x equals as x approaches -3. The other thing I want to point out, and this really is a notational issue, notice that on every line here I went ahead and wrote the limit. And the reason that you do that is because this was actually an operator. And you want to make sure that you maintain that operator until you actually apply the operator. So notice that I didn't drop the limit notation here until I actually plugged in the -3 and started evaluating that. So this is a relatively simple one, but it kind of gives you an idea of what we're going to be trying to do. We're going to be trying to simplify these functions to eliminate the point where there's an issue that's causing me to not be able to evaluate this up here. So that's kind of what we're after. And we're going to look at a few different ways to evaluate these things algebraically. Certainly not all of the possible ways, but maybe some of the more common ways that you can see this done. Okay, so this is how I would handle a problem like this. Let's take a look at another one. Let's say that I've got the limit as x approaches, let's do -2 this time, of x plus 2 over 1 over x plus 1 over 2. Let's say we have this problem here. Now, again, we can plug in if we want to. We can plug in -2. I would get -2 plus 2, which is 0. I plug in -2 down here. I get -1/2 plus 1/2. I get 0 over 0 again. So there's probably going to be some kind of algebraic way that I can simplify this to make this problem a little bit easier to do. And the way that I'm going to handle it this time is, obviously there's no factoring that can be done, but what I do notice is that I've got a compound fraction here. So I'm going to try to eliminate this compound fraction. I'm going to do that by multiplying the top and bottom by 2x. If I multiply top and bottom by 2x, and I'm allowed to do that, of course, because it's multiplying by 1, so I'm not changing the problem. And when I do that, I'm going to get the limit as x approaches -2 of 2x times x plus 2. And when I multiply the 2x over here times the 1 over x, the x's will cancel, leaving me with 2. And when I multiply 2x times 1/2, that's going to leave me with x. Okay, so we're getting closer to what we want to do here. I've got the x plus 2, I've got a 2 plus x down here. pretty close to what I want. I'm going to go ahead and reverse the order of those, and I'm going to take the limit as x approaches -2 of 2x times x plus 2 over, since addition is commutative, I'm going to write that as x plus 2. And now, because I don't care what happens at -2, I only care what happens around -2, I can cancel out that entire factor down there, giving me the limit as x approaches -2 of 2x, and that's going to be equal to, when I plug in -2, it's going to give me 2 times -2, which is -4, and there's the value of my limit. So again, just doing some algebraic manipulation on the problem, trying to figure out a way to eliminate the point that was something of concern to me. So that's how I handled this one. Now, I want to point out something else here while we're at this, and you can try this with your calculator. What I want you to notice here is that if you take our original function that we have right here, and you can do this with the previous problem as well, and really with any of them that we do. If you take this original problem that we have here, and you graph that, and then you take this function here and you graph that, what you're going to find is that the graph is going to be exactly the same. So if you graph this function, you're going to get a graph that looks exactly like this function. The only difference in those two graphs is that with this function, there's going to be a hole, which you won't be able to see on the graph. There's going to be a hole at -2. If you look at the table of data at -2, this one will have a value, this one won't. Okay, so that's what's happening here. And that's not surprising, because what we did was we eliminated the problem. And that's why we were able to go ahead and evaluate this thing. Okay, all right, let's look at another one here. This one may be a little bit more complicated, looks a little bit more difficult here. Let's try the limit as h tends to 0 of, let's do 4 minus the square root of 16 plus h divided by h. Okay, for a problem like this, again, first thing you want to do, plug in the value, see if you can evaluate it that way. If I can't, I'm done. If I can't, then I'm going to have to see if I can do some kind of algebraic manipulation. So I plug in 0 for h, and that gives me 4 minus the square root of 16 plus 0, which is 4 minus the square root of 16, which is 4 minus 4. So I get 0 in the numerator, plug in 0 in the denominator, and I end up with 0 over 0 again. So again, I'm in an indeterminate form. It's not undefined. Please don't say that's undefined. So there is probably some kind of algebraic manipulation that I can do here. This one's not nearly as straightforward. It doesn't seem very clear what we should do. But hopefully you remember from your algebra and pre-cal days the idea of multiplying by the conjugate. This is a good strategy sometimes, especially if you've got roots or radicals involved. So what I'm going to do here is I'm going to multiply top and bottom, again multiplying by 1. This time in the form of the conjugate, so I'm going to be multiplying times 4 plus the square root of 16 plus h over 4 plus the square root of 16 plus h. Okay. Now when I do that, of course I need to, this is a binomial times a binomial here. It is the difference of two squares, so the middle term is going to drop out, which is good, because that's why we multiply by the conjugate, is to make that happen. So when I take the limit as h tends to 0 now, 4 times 4 is 16, minus the square root of 16 plus h times the square root of 16 plus h is the square root of 16 plus h quantity squared, or 16 plus h. Don't forget your parentheses there, because we're going to have to distribute that negative through. And divided by h times, now on the bottom there's not a whole lot I can do here. I'm going to do 4 plus the square root of 16 plus h. And I can distribute the h if I want to. I don't really want to here, because that's actually the problem area, the thing that I'm wanting to get rid of here. So I'm going to take my next step, go ahead and, actually rather than rewrite this whole thing, I'm going to go ahead and distribute that negative, which is going to make the 16 minus 16 minus h. And now the 16s will subtract each other out, leaving me in the numerator with negative h over h times 4 plus the square root of 16 plus h. Now, the h's will cancel. That h cancels that h. That gets rid of my 0 in the denominator. It doesn't get rid of all of my h's in the denominator, but notice that when I plug in 0 here for h, I'm not going to get a 0 in the denominator as a whole. So it's not going to cause me a problem. So now that I've got that canceled, I can say, okay, that's the limit as h tends to 0 of -1 over 4 plus the square root of 16 plus h. And as h goes to 0, that's going to be -1 over 4 plus the square root of 16 plus 0, which is -1 over 4 plus the square root of 16, or 4. And so my limit here is going to be -1/8. Okay, so this one's a little more complicated, a little more detailed, a little tougher algebra to be involved here, but still just algebra. The interesting thing about working with these limits is that the actual process of doing the limits is just a lot of algebra. There's very little calculus involved here. If you'll notice that we have a calculus problem here, but multiplying by the conjugate was algebra, and then distributing the negative was algebra, or multiplying together and then distributing the negative was algebra. Canceling out the h was algebra. It wasn't until we got down here and I said, okay, now I'm ready to do calculus. The calculus was plug in 0 for h. That was all there was to it. So the calculus here was easy. This is one of the things I always like to say is calculus is easy. It's the algebra in calculus that's more difficult. So this is how we're going to approach these. These take practice. This isn't something that you can look at and say, okay, I know how to do this. So make sure that you go into those practice problems. Make sure that you get plenty of practice with these things. Look through the solutions if you have trouble with them. And then once you get comfortable with this, you can see that it really is just a lot of algebra with just a little bit of calculus at the end. Hopefully this will get you started with things, and things will go smoothly from here. Look forward to talking to you about continuity in our next video.